the
Yeah.
following one, do you do it cumulative or do you do it?
I mean, so the answer is with all of chemistry, it's always cumulative. Now, I know that's not really what you're asking. What you're really asking is there going to be material from like chapter 13 on the second exam? The direct answer is no, but as you'll see when we get to kinetics, equilibrium, it's based off of kinetics, right? Kinetics is part of it. So I'm not going to go back necessarily to those other chapters and pull a direct question out there, but the concepts, that kind of idea is from there, right? So, yeah, what's up?
I feel like the potentially useful like sheet
Yeah.
is on campus.
I don't know if I have one for the second semester here. I should probably throw one together for you guys. Yeah, because it's not one of those things where I really don't need you guys memorizing equations, right? Like, I'm not gonna expect you guys to like have memorized like the integrated rate laws. Like, what's the point, right? You know, I have to look them up, right? And you guys, why not? Like, you got the book and it's in there. I think is this the book that, I didn't bring it with me. I can't remember if it's this book or one of the other ones, but one of them actually lists all the equations at the end of the chapter, like right before the end of chapter problems, right? So those are the ones that I always give to you guys, is what it is, right? I'm not really interested so much that you guys can memorize an equation. I'm interested, can you guys understand the equation and use it? Do they have it there? Yeah.
It says key equations.
Yeah, cool. So, but yeah, I will give that to you guys, but do me a favor, send me an email to remind me to put that up there for you guys, because within like the next 30 seconds, I'm gonna forget what you asked, okay? But it's nothing personal, right? So, but yeah, I'll give that to you guys. But yeah, okay, so I think that's that. I think that's kind of all I have to chat with you guys about. Can't think of anything else, but if something comes up, I'll post an announcement. Oh yeah, that's what it was. Laura posted an announcement for you guys about the exam review, right? Kind of what I mentioned there on Monday for you guys. The best way to actually take advantage of those reviews is to walk in there with some questions, right? Some pointed questions. What is not a pointed question? Hey Laura, I don't understand anything about kinetics.
It's kind of pointed.
There's nothing, no, it's not, right? You guys know something about kinetics. If you walk in there and say, well, I don't really understand how to, what an instantaneous rate is, that's a good question to ask, right? So something like that, right? But if you just walk in there and claim not to know anything, then, well, there's not really much anybody can do, right? I know you guys know some of this stuff, right? So work some problems in the back of the book, and if you can't solve one, then go in there and ask Laura, hey, can you work through, problem 14.34 or whatever it is, right? And that'd be something good to kind of ask and walk through with that stuff. All I'm saying is the same thing you guys already know, right? The more effort you put in beforehand, then the easier it is for you guys to get the help that you need. That's all it is, right? So, but you guys know this, you guys have made it this far in your academic careers already. Okay, I think that's kind of it. But, yeah, any other questions then before we kind of head on into it? All right, yeah, what's up?
How come we don't get Jolly Ranchers?
How come you guys don't get Jolly Ranchers? I'll bring them for you guys. How's that sound? Cool. All right.
Weird Jolly Ranchers.
Hmm? Oh, I give it to my organic class because I like them better than you guys.
Wow.
I'm just being honest. I'm joking. I will
Is it
bring.
just because they're smarter or you've known them longer?
Or because they have to endure more.
Well, there's only 10 of them. I have to be super nice to them. Like you guys, I can still be mean to, right? Because there's a lot. No, that's not it. No. It's just, no, I don't know why I didn't bring them to you guys. I don't know, do you guys really want Jolly Ranchers at 8 a.m.? It puts them in my coffee, mix it up, right? I got blue raspberry Jolly Rancher coffee. Sounds disgusting, okay. I will bring them. Great question, thank you. Alrighty, anything else? Yep.
What kind of candy do you find best in the morning?
Give me the nothing in the morning, right? But in general, the more sour, the better for me.
So you're a sour punch kids guy?
Yeah, they kind of tear apart your, like you can only eat like 3 of them before they like tear apart your mouth, so. But that's just,
Hey, no pain, no gain, like my mom says.
yeah. Anyway, yeah,
Are your exams on paper?
I hope so.
Yeah.
Yeah, I'd rather not do the online stuff. At the moment, I don't think there's anybody missing from class, right? So we should be able to do it all on paper. I'm not a big fan of the online exams, just because it makes it Wow, there's a lot of anyway, I don't need to go into that at the moment, but if something changes, I'll let you guys know about it. At the moment, we'll be doing it during, the lab time. Anything else? Cool, alright, so, let's get started with prayer then, and then we'll, have I think 1 or 2 practice problems here, and then we'll get into it. Lord, we're here yet again, and we just thank you, Lord, for the gift of another day, and just the gift of another chance. And Lord, as always, we just pray to be the good and faithful servants that you ask us to be. And Lord, we just pray that we can work towards you and work towards your kingdom today, whatever way that is. Lord, but also keep us humble. Let us know that it's not our works that bring us any closer to you, Lord. It's our faith and our love that we can show for you and for others around us, Lord. So just increase our faith today. Just help us to understand what it is to love others as you love us, Lord. Just pray that you clarify this in our hearts and our minds, Lord. And we just pray this in your name. Amen. All right. So, let's do a problem here. So let's suppose, get a little bit of a bigger size here. So let's suppose that we have a reaction or an equation, right? N2O5, 4NO2 plus O2 here, right? And suppose that we know that this is a first order reaction, okay? And we did some work ahead of time. We know that the rate constant K is equal to 6.82 times 10 to the negative third inverse seconds, 1 over second. And we start a reaction with 0.025 moles of N2O5 in a 2-liter, right, volume, or whatever you want to say, right? So that tells us that our initial concentration of N2O5 equal to 0.0125, right? Got it? So we have a reaction, we have a K, we have an initial concentration, we have an initial amount, and we got the volume of the container that we're in, right? So that's all that is. So, question, how many moles of how many moles of N2O5 exist after 5 minutes? Okay. So how many moles of my starting material exist after 5 minutes of this reaction? So you guys will need a couple of equations and stuff from your notes there. Yes, ma'am. Molarity. Yeah, that's capital M. While you guys are kind of jotting down and thinking and panicking internally, as with most of the problems that I give, right, these are all from the back of the book, okay? Now, the difference is when you read this problem at the back of the book, they have a lot of other gobbledygook that they put along with it, right? And so one of the challenges with these types of problems, and one of the things to pay attention to and start to learn, is kind of how to draw the relevant information out of the problems in the way that they ask them, okay? One thing I don't like about some of the way they ask problems is they purposely try to obfuscate like what they're trying to get you guys to look for, right? They make it trickier than it needs to be, okay? But kind of remember how we approach this stuff in class, right? We always write out the given information, we find the equation that we need, and we start to plug in the variables. to get the stuff taken care of. That's all it is, right? No matter how complex the question might be worded, just write out what you have. Mhm.
Hey Doc, I know this is probably a really stupid question, don't we need the Halflife link or the wait, no, we don't. Whatever. I don't know what I'm doing.
I think it was the right path, but that is part of the question, right? What do we need, right? What do we need? This is the kinetics. Yeah, so it should be 14. So, right, so what information you have? You have that, right? You have that, you have this, right? Yeah. And I ask you to do that. So, got it?
I don't know if we can start with that thing. I don't know if we sometimes the concentration of one of the products and like throw that into the rate, the actual equation.
So what's, ignoring all the numbers, what is this question asking me to figure out?
How many, what, something,
After an elapsed period of time, right? What's the only set of equations that we learned?
rate correction,
Hmm?
the rate.
Well, the integrated rate laws, right? Remember, integrated rate laws are how we can calculate the change in concentration over time. Yeah, it is. What's the equation for the integrated rate laws?
K times.
Looks good. Keep going. Looks like you're on the right. Mm-hmm. Pardon? I'm sorry, so. Well, you have to get rid of it, right? So it'll E to everything. So what is this problem asking, right? It's asking to calculate how much of something, or how much of something you have after an elapsed period of time, right? A change in concentration after a given amount of time. Right, that's what this is asking, right? What's the only set of equations that we have to be able to describe something like that? Our integrated rate laws, right? Because our integrated rate laws are ways of relating the initial concentration to some concentration after a specified amount of time, right? Oops, I forgot my computer is being dumb. So you gotta be a little bit smarter than it. Okay, so our integrated rate laws for a first order reaction this. Right? The natural log of the concentration after some amount of time is equal to negative times the rate constant times the time times the natural log of the initial concentration. Do we have initial concentration? Yep. Do we have time? Yep. Do we have a rate constant?
Yes.
Yep. So can we calculate the concentration after a given amount of time?
If we have brain cells,
Yeah. Right?
but I don't.
I think they're there. So one thing to pay attention to, right? So take a look, what do we have here? 5 what?
300 seconds.
Minutes. What are our units for K?
Seconds.
Inverse seconds, right? Over seconds. So we need to make sure that we have everything in the proper units to kind of get everything worked out, right? So we don't care about 5 minutes, we care about
300 seconds.
300 seconds. You guys with me on that? Okay. Oh, goodness. What's nice is when software updates and then changes everything. Okay, here we are, right? We're making it happen. Negative 6.82 times 10 to the negative third inverse seconds. Our rate constant K, which was given, right? 300 seconds, our conversion of 5 minutes, right? Plus the natural log of 0.0125. Got it? Not too bad, right? It's all given information. The only thing we have to really pay attention to is the units with the rate constant and what information they give you there, right? Because you plug in 5, you're going to get a completely different number, right? All right, so if I did my math properly, this is the natural log of, I guess we can go ahead and write this out, the N205 at that time is equal to negative 6.428, right? And to get rid of the natural log, just take everything to the E, right? So E this side and E that side there. And so my concentration of N205 at that time would be equal to, what did I get? 1.616 times 10 to the negative 3, right? Good?
Something like that.
No, did I do something wrong here with my math?
Did you do the national log of 0.0?
Yeah, I thought I had. Let me check, let me see. I got, for this over here, I got negative 2.046. And this is the negative 4.38. Or did I plug something wrong in my calculator earlier?
Looks right to me, Doc. I came out.
So those two, then this, and then E to the, maybe I just typed in this wrong. So what's, you guys got this then?
Yeah.
Yes.
And then E to that is not equal to this? Oh, it is, okay, all right, what's up?
I got that, but it just, like, it wasn't like times 10 to the negative third, so on the test, if we have something where it's like, the answer's 0.0001, like, 16, like.
That's the same thing, right?
Yeah, but
Yeah.
do you want us to like?
I don't care.
You don't care?
No, just put it, I know what, I don't, that's not what I'm interested in you guys doing, I'm interested, can you get to that answer?
Okay.
Because you're representing the same thing, right, just one scientific notation is all.
Hey, Doc,
Yeah,
how do we do the E thing?
should be under calculator, usually it's above the natural log, right, so right up there,
Oh,
yeah, because they're the opposites of each other, that's usually the calculator laid out. So, are we good, we're done, yay?
no?
No, because what did the prom ask for? Not the concentration, but the moles, got it? So I know, remember, these are one of these things that I'm always asking you guys to pay attention to. We're happy that we got a right answer, right? Our math worked out, it seemed a little bit easier maybe than initially expected, but always go back and check to make sure you're answering the question properly, right? So it says it wants how many moles. We have units of what? Moles per liter. So what do we need to do? Multiply by 2 liters up there, right? And then we're ending up with units of moles. So our answer should be what? 3.2 something times 10 to the negative third, right? So moles of N205, right? 2 liters, basically 3.2, right? Times 10 to the minus third moles. How many times have we worked a problem like this now in class? 3, 4 times, something like that? You think it's important to be able to do those? Yeah. What's up?
Question. Can you scroll up for a second?
Yeah.
Because the part,
Start a reaction or whatever.
0.25.
Oh,
Not
no. In 2 meters.
So then,
Yeah.
We're using the molarity, the two
Yeah.
liters tells us how much volume we're working.
So we can convert between moles and liters, is what it is. Or moles and molarity.
oh,
Yeah.
oh, it's just.
Yeah.
Okay.
What's up?
Is this gonna be like the same though, see on test from?
Sure? I don't know, I'm not sure what you're asking.
Like, is like how hard this is, whatever, is trying to test how much we need, hardness of this, like,
My problems come from the book, right? So, are they gonna be verbatim copies of the book? In some cases, sure,
so it's gonna
right?
be there.
Am I gonna change some things around but have the exact same ideas, maybe asked in a different way? Absolutely, right? Yeah, I can't get that creative with Gen Chem 2. There's only so many ways I can ask how do we calculate the change in concentration over time, right? So, all right, cool. Next question, what's the half-life of N2O5?
We're supposed to know that?
Yep,
From that, from what we did?
sure. So what am I asking you when I say what is the half-life of whatever? The time that it takes to get the concentration of 1/2 of whatever the initial thing that we started at, right? So I'm saying calculate T1/2, right, which is equal to what?
Natural log of 2.
Natural log of 2 over K, right? You guys with me on this?
No.
What's it? Well, the natural log of 2 is a constant, right? It's whatever 6 or 0.693 or whatever it is there, right? And what's K?
Why is it natural log of 2?
So if you plug in the values into your first order rate law there, right? One of them is the initial concentration, the other is half of that. And when you rearrange and bring it all together, it solves out the natural log of 2. Right? I think that's what I saw you doing, right? So, yeah, basically if you combine these together, right, you'll get, that'll end up being just the natural log of 2 there. No. So I showed you that derivation in my slides, right? So it's in there if you want to take a peek at it. You can do it that way too and just plug in the numbers, right?
Is it the negative? No. Oh, because K, okay.
Yeah.
Gotcha.
Yes.
Wait, how'd you get that? Like, I'm like reading the slide, but like, did you like solve to get
just T 1/2 equals that.
Basically, yeah, we took that integrated rate law and solved it for a half-life.
Okay, so that's just the given formula.
Yeah, I showed you the derivation to get to this in my slides.
Right,
so
okay.
too. Yeah.
So on an exam, that's the only part of the thing that we should show.
What?
So like, if we were to work out problems, we don't need to.
If I ask you this problem, yeah, that right there, right?
Okay.
Yeah,
You put that in there.
sure. Right? So natural log of 2 over k, do we have k? Yep, so is this pretty easy? Yeah, did it sound scary? Yeah, is it gonna be scary anymore? No, because now you guys have seen it, right? Like, oh yeah, this is easy. What changed? Why did it become unscarier? There you go, right? I know, I promise, I've told you guys this before, I'm not just saying this because, you know, I'm trying to be cool or whatever, like, this stuff was scary to me also, right? The only difference is I've had more experience working through this stuff, okay? That's all it takes. Okay? What's that?
Since this only works for first order reactions, right?
Hmm,
Would you try to trick us and?
absolutely, but go ahead and finish your
A
question.
different order reaction and then ask us if it happen?
Okay, so here's what she's saying, right? What if it wasn't a first order reaction? How could we solve a problem like this? Well, when we specifically say the half-life, we're saying it's defined as a first order reaction. If we back away from that and I ask you, how long would it take this to get to half of its initial concentration? What does this become then? It becomes just like part A, right? Where we have to use one of our integrated rate laws to figure out what the concentration is after a given amount of time. So if it's not first order, then it's either 0th order, which has an integrated rate law, or second order, which has its own integrated rate law. So you just plug in and use the values the same way there, right? Does that make sense? The reason why we got to this is because we used our first order integrated rate law with the assumption that we have an initial and half of that. And it just solves out to this right here. That's all it is.
Okay, and in problems, are you gonna tell us what order?
I have to, right? I have to specify that. Otherwise, you guys don't know, like, okay, is it 0 for, unless I say something like this is an elementary reaction, right? Because elementary reactions are, there's, when I say something's elementary, that means it is expressed as, right, a first order elementary reaction, or excuse me, a unimolecular elementary reaction is always first order, a bimolecular is always second order, right? And so take a look at what that's in my notes, and it's also, there's a couple problems in the back of the chapter that say, hey, this is an elementary reaction, express the rate law for it, right? And so just asking you to kind of practice that idea there, right? So if I have to give you some information about the reaction itself, for you guys to figure out what the order is, right? If you don't know what the order is, then you can't really approach this, right? But a good question, yes?
How do I identify a 0th reaction?
I'll have to tell you that, right? I have to tell you that, or I can give you like the graphical representations here, right? Remember, if I give you graphical representations, the one that has a linear relationship tells us what the order is, right?
They all want to
That's the point, right? There's another example in my slides that I graph one rate or one set of rates for all 3 different methods, and only one of them comes out linear, right? That's going to be your rate law then. Yeah.
Why do we not like deal with the two, the stoichiometry like in any way in either of these problems?
Why do we not deal with stoichiometry?
Yeah.
Because the rate isn't dependent on the stoichiometry in that way, I guess. It's a very, so the answer is thermodynamics, right? And it gets kind of complex very quickly, right? And to be honest, like I don't remember the exact way to get there, right? I genuinely don't. It's not really something I deal with on a day-to-day basis. I remember there was some partial derivatives and all this stuff kind of falls out and blah, blah, blah. I can look it up for you and I can send that information. I know you don't want me to, and I'm not going to, but I promise there is a rhyme and a reason behind it that's mathematically provable. I don't have it off the
So
top of my head.
we never use them.
Not for rate laws, right? When we get to equilibrium, then yes.
Okay.
And the answer there is going to be based off of the same thing that we're talking about here, right? I thought somebody else had a question, but. Cool. One more? Okay. bit different one, kind of based off some of the stuff that he did towards the end. So assume we have a reaction, a set of elementary reactions. So H2 plus ICl goes to make HI plus HCl. So assume that we've been able to break down a complex reaction into these two steps here, right? So question one, the best question to always ask is, write the overall balanced reaction. Or balanced equation, I should say. Equation. So here are the mechanistic steps for an overall reaction. Tell me what the overall reaction is. That's what this is asking, okay? So when we're asked something like this, what do we need to do? Just add up the stuff that's on the left side of the arrows, right? Add up the side that's on the right side of the arrows, and just cancel out stuff that exists on both sides, right? It's not that bad, right?
Huh?
Just add up the stuff that's on the left side of the arrows, right? H2 plus ICl plus HI plus ICl, right?
I'm
You guys
so
with me?
confused. No,
Yeah.
you lost me.
No, this is just like step by step.
HI plus HCl plus I2 plus HCl, right? You guys see what I'm saying? Just adding up everything on the left and the right side of both of those arrows. Now what do we start to see? Well, we got H2, ICl, HI, ICl, right? So we got two ICLs, we can bring those together into one expression, right? We got ICl, we got ICl. Over here, we've got HCl, we've got HCl. We've got HI over here and HI over here. So what do we see when we have HI on both sides of the equation here, right, or both sides of the arrows? They cancel each other out. That also tells us what? What is HI?
Intermediate.
It's one of our intermediates, got it, right? So this was the next question that came out of this problem in the book, right? But this is, I'm not gonna write that down, but when you start to cancel things out on both sides of the equation then, right? It's probably an intermediate, okay? Cancel that out, cancel that out. And so if you want to simplify everything down, H2 plus 2ICl goes to make I2 plus 2HCl.
So,
Good?
is there a potential problem, is it okay to just like take the first bit of the first line and the last bit of the last line? Just put those together and balance it?
Would that happen here?
That's what I did. I took H2 plus ICl becomes I2 plus HCl,
Mhm.
and then I just balanced it.
It might, right?
It
What
worked.
if something isn't an intermediate gets produced along the way also? A side product, right? What if something doesn't cancel out in between this? Now your question comes back to, there has to be, the laws of nature have to be kept, right? We can't create or destroy matter. But necessarily, what does it all turn into? Are we saying that your assumption is that all the chlorine ends up as HCl? It might not, right? There could be something else that's produced along the way also. Do you get what I'm saying with that? So in theory, yeah, that works for most of the time, but we always have to just be careful of it, right? Right, so if we cancel something out in green, that's our intermediate. The question then asks, what is the rate law? Assuming the first reaction is slow. So what's the rate law, assuming the first reaction is slow?
It'll be the rate law of the first reaction.
Mhm.
Don't we need more information about the speed of this?
Can we find it without concentration?
Aha. Alright, so here's what you guys are asking. So I'm telling you that this is the slow step of this reaction, right? So if you guys think about it, right, a rate law is just equal to rate, right? K, the concentration of H2 to the M, right? And the concentration of ICl to the N, right? That's any rate law. That's pretty much all we need to know about, right? For what we can tell. But what's missing from this? The M and the N. Got it? Now here's some information that will make this able to actually be solvable. So if we know that these are elementary steps, what does that mean M and N have to be?
2. Wait, no, they have to add up to.
They have to add up to be equal to 2, right? Why? For an elementary reaction, that's bimolecular. How do I know that this is bimolecular? There's 2 parts of it, right? What are the 2 parts? This and that, right? For an elementary reaction that's bimolecular, the order has to be 2. Got it? Remember, the overall order is what? M plus N plus whatever, any other parts you have there. So if I know an elementary reaction that's bimolecular, it has to be equal to 2. Therefore, M and N have to be equal to 1 each. Got it?
Couldn't you have one be 0 and the other be 2?
Hmm?
Couldn't one be 0 and the other be 2?
No. Well, let me think here for a second. I don't know if we have enough information to make that statement, I guess. Good question. Let me think about that a little bit more.
Because
I
one
feel
of
I'm
the
just,
earlier problems we worked, we had a second order and one had a 2 for M. and
when we had other information for that, right?
I don't remember where it was.
Yeah, I don't think we declared those as elementary necessarily, though. Good question, though. Cool. All right. So, what do we say about these types of things here? Right? What if I said the second part of this was slow? Right? What do we have to pay attention to with those types of questions? Well, remember, the slow step is what we write the rate equation for. Right? And if we have part of our rate expression an intermediate, we have to go back and rework that to get it into concentrations based off of things we can measure. Okay? So take a look at the example that we worked through in the notes there for that one. And we rearranged the equation to get this into something that we can actually measure, right? We can't really measure intermediates is what the problem is. Okay? But those are really the questions that come out of these types of mechanistic type rate laws. Okay? Yeah?
So then would the answer for this be with M and N, or would you like us to put
1 and 1. Yeah, that's not a completed rate law there, right? We need to figure out what M and N are. So I either have to give you information or tell you guys that this is a elementary reaction, right? What's up?
So anytime there's two parts, in other words, they're bimolecular, M and N will,
If it's elementary.
if it's elementary.
Right.
Okay. And you told us that it was.
I told you guys now.
Okay.
Right. Yes.
Can you give us an example if it's not elementary?
I would have to tell you something about it, yes.
Oh, gosh.
Again, there's no real way for you guys to look at that and say, yeah, I know this is elementary or not, right? Because remember, I think the first or second slide of this chapter tells you guys important information, right? The rate laws have to be derived, right? We have to actually measure them. We can't just look at something and assume what it is. Unless I give you some information about the specifics for that reaction, right? Yeah, what's up?
You already said this, you said, so if you instead told us the second part of the equation was this low one.
We'd have to go back and just rearrange some stuff with that. It doesn't work out for this one here,
For
right?
the intermediate, that's why.
Yeah, we can't express a rate law in terms of, or we shouldn't express a rate law in terms of something we can't measure, right? We can measure things that we put in, right? We can measure initial concentrations,
Okay.
right? That's what we say with that. So really, we're just rearranging to get everything expressed in H2 over ICL. Right? But there has to be a little bit different of a setup. So the difference is, take a look at the example that I put in the notes there, right? We have the idea of K1, K minus 1, all these kind of things that come from that. Okay. Cool, all right.
Can K prime ever have a numerical value?
Absolutely, right? It's just a rate constant.
But is there any good way of determining that?
Yeah. Math. Pretty good way. Okay. So we get into one of the most important ideas out of Gen Chem 2. And that's this idea of equilibrium. Now, all that equilibrium is for us, right, is going to be a way that we can, well, I should be careful, right? There's a lot of things we can do with it. What we're going to learn then, let me restart this here. What we're going to learn in this chapter is to be able to calculate the concentrations, right, of a reaction and kind of tell whether the reaction is still progressing forward or whether the reaction is going to progress backwards. Okay? Now I say, well, what in the world does that mean? Well, I think equilibrium is one of these terms that we've all kind of heard of, right? We use it colloquially in some terms, right? Or in some ways. And so we think of it as a balance, right? Everything's in equilibrium, everything's balanced. And that's true for chemistry also, right? But what is balanced? I'm not saying the concentrations are balanced, right? They don't have to be equal to each other. But what it is equilibrium is when the rate of the forward reaction and the backwards reaction, right, are going to be constant. The concentrations aren't going to change. Do you guys catch what I mean with this? The concentrations of the products and the reactants aren't going to change. They just kind of plateau off, okay? Now this is an equilibrium constant. Got it? That means if I perturb my system in some way, that constant has to be reestablished, okay? And that brings us into this, probably the second most important idea that comes out of this chapter, and that's what we'll talk about, Le Chatelier's principle, okay? So every reaction you guys have done in the lab, every reaction that I've ever done in the lab, we're fighting with equilibrium. Now the good news is we can control it, right? And I'll give you guys some examples of this, right? How can we kind of tame equilibrium and have it favor what we want it to make rather than what the laws of nature dictate, if you want to think about it like that, okay? So here's what we're going to learn. We're going to learn another K. In fact, we're going to learn 2 Ks, right? We're going to learn Kc and Kp, right? The equilibrium constant for concentration and the equilibrium constant for pressures. Now, they're going to be related to each other. There's not really going to be a huge difference in between the two, right? It's just we have to pay attention to whether we're dealing with solutions or whether we're dealing with pressures. That's all it comes out of, okay? Both expressions of K are going to be the same. It's going to be products over reactants, okay? That's all it is, the concentrations of the products over the concentrations of the reactants, right? And we're gonna have to bring the idea of stoichiometry back into this, alright? Now, the third thing that you guys are gonna learn out of this chapter is what's known as ice tables. And ice tables suck, right? Right? But there are a way of setting up the math that we need to be able to calculate the either equilibrium concentrations, the final concentrations, how much gets made or exchanged in between while a reaction's going on, all these kind of things, okay? And we'll walk through how to go through, or I'll walk you guys through how to set up the ice tables. They're not that complex to do, right? The problem is when we set up ice tables, we might have to solve a quadratic formula. And when was the last time you guys did that? Never, okay. Right, you did it in algebra, and then it took a long time, and then now we're here, right? So we'll go through an example of, the quadratic formula and how to solve it. It's miserable, it takes a couple pages. I always end up dropping negatives and positives, and so and I end up getting, the wrong answers sometimes, but we make our way through it, right?
Still less painful than this one.
Completing a square is easy, just draw another line, right? Alright. So, let's start to think about some of these ideas then, right? So, many reactions fail to go to completion, aka they're not going to exactly get to 100% yield, that kind of thing. The concentration of the reactants stop, the concentration of the product stop increasing, blah, 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 right? Now, a couple of terms to think about here, right? Some things that we start to talk about in the lab, or we see written down in the book, or in some journal articles, things like that. If there are more products than reactants versus the other way around, we just tend to say product favored versus reactant favored reactions, right? Obviously, for the most part, we always want to do product favored chemistry. Otherwise, we're kind of, fighting the tide, so to speak, right? But just some ideas there, right? Here's another wall of text, lots of walls of text coming at you at the start of this chapter here, but some ideas and thoughts on paper. So assume we have that reaction up there, right? We've seen that quite a bit. We see the double-headed arrows in between there, right? You're going to start to see those over and over and over and over and over again, okay? That's going to be what this chapter is kind of about, right? Dealing with the equilibrium. So the idea is A plus B makes C plus D, but C plus D can come together to make A and B again. Right? So we have the two directions that this reaction is going, okay? So here's what I was trying to say earlier, right? So equilibrium occurs when the concentrations of those stop changing. I'm not saying the reaction stops, because A and B are always making more of C and D, but C and D are always making more of A and B, right? The concentrations don't change. Not saying the reaction stops. You guys catch what I mean with that? Right? It's a subtle difference, but it's important to kind of define what we're doing here, right? So what do we mean by dynamic equilibrium? Well, that's kind of that old stuff there, right? So the species don't stop forming, the rate of formation equals the rate of removal, right? You guys catch that? This is where K's come back into this. K1 is equal to K minus 1. The rate forward is equal to the rate back. Got it? Concentrations are constant, products are being made, the total amount doesn't change, neither product can escape the system. That's kind of an important definition, although we can actually, we can't escape the system, so to speak, we can play with this idea a little bit, and we'll come back to that with Le Chatelier's principle, okay? And the ratio of concentration terms is constant, okay? That's where we get our big K, our equilibrium constant from, okay? The ratio of the products for the reactants. So if we take all those ideas and kind of graph it all out here, right? So we have concentration on the left there, rate versus time, concentration versus time, right? So as the system approaches equilibrium, both the forward and the reverse reactions are occurring. Got it? At equilibrium, the forward and reverse reaction rates are proceeding at the same rate, okay? And once equilibrium is achieved, the amount of each reactant and product remains constant, right? So I'm just taking the exact same ideas from the previous slide, I'm just graphing them out for you guys, so that's a little bit easier for you guys to visualize it, right? After a certain point, reactions, the concentration doesn't change, and the rates become constant. Good? So what we're gonna start to figure out is, where do we line our reaction? Are we before or after equilibrium is reached? Or how can we influence and move our concentrations, okay? So we're gonna kind of hop around different parts of the graph, might be another way of thinking about this, okay? And here's just a different example, kind of put out a little bit differently, if this helps you guys out. What we're saying here is, I can start with my products, right, and I'll come to my equilibrium, or I can start with, I can start with my reactants, achieve equilibrium, I can start with my products, and achieve equilibrium. Right, and there's actually a pretty good lecture for this online, where a guy kind of talks a lot about, this is the Haber process, which is one of the most important kind of chemistries to come out of the 20th century, in many different ways, right? But anyway, so they just talk about how industrially equilibrium affects the process here if we have producing ammonia, right? So we can't escape the equilibrium concentrations is all we're saying, although we can start to push things around a little bit, is what we will get to, okay? Now here's something interesting. Catalysts do not affect equilibrium concentrations. Interesting. Catalysts speed up the forward reactions, but they also speed up the reverse reactions. So what do they really do? Well, all they do is change the time needed to get to equilibrium, okay? So there's an interesting thought of this.
So there are no catalysts that only speed up one process without?
Well, equilibrium is equilibrium, right? Now again, we're gonna play on this a little, I'll answer your question as we go through this, right? It's a good question though. All right. So let's see if we can figure out a little bit about the equilibrium constant. So assume we got the forward reaction there, right? N2O4 goes to make 2NO2. We can write a rate law for that, okay? We have the reverse reaction. All I do is flip that around, right? And I can write the rate law for that. Got it? At equilibrium, the rate forward has to be equal to the reverse rate. So I can just set those two expressions equal to each other, and I can rewrite this, right? And then this becomes a constant, is what it is. Got it? I can express my equilibrium constant with respect to, right? With respect to the concentrations of my two components that are in there. Yeah.
It's not, it's a different constant than what we were talking about with the concentration rate,
Yes.
integrated rate law?
Yeah.
Okay.
Is
Good.
it still gonna take the same form of moles per second? Or, not moles per second.
Good question. I'll answer that in just a second. Okay. So if we take this exact same idea and kind of just a different reaction, right? We just say the rate forward has to be equal to the reverse rate, right? We see how equilibrium is achieved there at a specific concentration. Right? So we take those ideas again, rearrange it, right? So our Kc, right? Concentration of our products over our concentration of our reactants, okay? And that's what it is, right? Whenever I ask you guys to write a equilibrium constant, it's our products over our reactants, okay? And we can actually get a numerical value out of this if I give you guys information about the concentration. I know what you guys are thinking, like 1.65, holy crap, what does that mean, right? That's what we're gonna figure out as we go through it, right? That K, that capital K, can be a huge number or it can be a decimal. And that tells us something about what's going on at equilibrium, okay? Good? Not too bad so far, right? So if we have a generic reaction, as we start everything out with, or as we want to go forward with this, or as we tend to write out, right? Is this? Ooh. Kc, right, is equal to our concentration of our products raised to their coefficients for a balanced equation. Okay?
You multiply them.
Mm-hmm. So we need a balanced equation. This becomes part of our equilibrium expression. Okay? That's it. Products to their powers over reactants to their powers. So why do I have like 40 more slides to go through? Huh?
It's complicated.
Because it gets a little bit tricky, but this is it, right? So whenever I ask you guys a question out of this chapter, this is kind of where we have to start looking to get to our answer, right? So much like with rate laws, how rate is always equal to K times blah, 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 right? Here we've got another K times blah, 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 right? Just a little bit different expression. Still dealing with concentrations, okay? Still dealing with balanced equations. Good?
So the exponents are just the balanced coefficients?
Yes, they are. All right, so this seems like a good place to kind of pause for the day. Tomorrow, don't forget, you guys have the exam review with Laura. I think she posted the time online, the time and the place, right, for you guys. So if you want to go to that, there it is. It's not required, of course. But I will see you guys on Friday.
What?